All right, here's part 2 of the Newton's second law for rigid body motion. We'll do some more examples. This is an example out of Beer-Johnson. I recommend that you buy the book. But let's go ahead and go through it. All right, so we have a pulley that's got two weights attached to it at two different radiuses. And the radius of gyration of the pulley is 8 inches. It's a 12-pound pulley. And we're assuming no friction at the axis. And we want to find the angular acceleration of the pulley and the acceleration of each block. I'm going to go ahead and get out of the way the moment of inertia of the pulley. They gave us the the radius of gyration. So we take the mass of it, which is 12 pounds, divided by 32.2 to get slugs, and the radius of gyration, which was in inches, and we wanted in feet squared. So we end up with a 0.6. Let me erase that. It's been a long time. All right. 1656, and that's a slug feet squared. We could do an analysis of this, so first a quick static analysis. Of course, it's not static, but we could do an analysis to see what's the difference between the moments so that we could determine which direction it's going to move. We could do that in our heads. We could see that for mass B, for block B, it's going to have a moment which is 10 times 6, so it's going to be 60 inch-pounds going counterclockwise. And then for block A, it's going to be 5 times 10, so it's going to be 50 inch-pounds going clockwise. So the counterclockwise block is going to rule, so it's going to rotate counterclockwise. Also, to start with, we could relate the kinematics between the accelerations that are going to happen at A and B with the angular acceleration. So in equation form, that would mean that the radius right here of the pulley, RB, times the angular acceleration is going to be equal to the acceleration B. So we're going to keep this in feet, so we'll say 6 divided by 12 alpha. And likewise, block A is going to have the radius of A times alpha, or 10/12 alpha. Now let's start with our free body diagram and our inertial diagram. Should have left more room in here. So inertial body diagram. And for this particular topic, we're talking about a system of rigid bodies. So we're going to include the blocks in these. And I'll switch colors here. Let's go green. No, I'll go blue. The forces that are being applied onto the free body diagram are the reaction forces Fy and Fx at the pin. And we're going to have 10 pounds at block B. On block A, it's going to have 5 pounds coming downwards. Block, let's see, I can switch colors again. We'll go purple. Beautiful. Block B has inertial properties here, or inertial forces of mass of B times the acceleration of B. And the block at A, though, is going to be going upwards, so it's going to have the mass of A times the acceleration of A. We're also going to have inertial acceleration by way of the moment. The moment let's see, angular inertial acceleration. Oof, I'm tired. All right, so we take the moment of inertia times alpha right here. So now we can write out the equation that the sum of the moments about g, the center of gravity g, is going to be equal to I alpha, that I is about g. But we should recognize that this term right here is all of the effective inertial moments, okay? So keep that in mind. We're going to treat counterclockwise as positive. All right, so the moments on the free body diagram are going to be 10 pounds times the moment arm right here, which is 6 divided by 12. That's positive because it's counterclockwise. We're going to have 5 pounds times 10 divided by 12 in the clockwise direction, so it's negative. And that's going to do it for the free body diagram, the external forces. Now for the inertial diagram, we'll take the moment of inertia, I alpha, so we have the value 1.1656 alpha, and we're going to add in also the inertial moments that are caused by this mass times acceleration. In other words, in the positive, because it's going counterclockwise, mass of B, which is going to be 10 divided by 32.2, times the acceleration, AB, is going to be acting with a moment arm of 6 divided by 12. Okay, so it's not only is the mass times acceleration, but it's also times a moment arm, because this inertial force or effective force is acting through that moment arm. Likewise, we're going to have the mass of A, which once again, I've not left myself enough room. So we're going to have 5 divided by 32.2 and times the acceleration at A times the moment arm, which is going to be 10 divided by 12. Okay, so now we have everything that we need, or do we? We have one equation and 3 unknowns. But remember, we went ahead and established our kinematic relationship. So let me plug those back in. I'll go down a little bit here so I could write the whole thing out horizontal. And I'll repeat much of what I've written here. All right, so now I'm going to substitute AB into there. But first, I'm going to juggle it just a little bit. So I'll go 10 divided by 32.2. That's the mass. I'm going to move over the 6 12s over here. And now sticking in the alpha in there is 612 times alpha. And then I'll also go the same over here, 5 30-seconds, 5 divided by 32.2 times my 10 over 12 times RA times alpha, which is 10 over 12 right here, alpha. Something that we could notice that's important is that this right here is I, this right here is M, and this right here is, we could call it R squared. Same thing here. This is M, and this is R squared. So what we've done here, in essence, is we've assembled the total amount of mass moment of inertia of this whole system by way of doing that. If we were to factor the alpha out, we would see that's what we would come up with. So we solve for alpha, and we get 2.373 radians per second squared, and it's going to be counterclockwise. So that's one of our answers. And then we could plug back into these equations up here to find that AA was going to be equal to 1.978 feet per second squared, and that's going to be moving upwards. And AB is equal to, let's see, did I write that right? Yeah, 1.187 feet per second squared, and that's going to be going downwards. All right. Now, we'll do this other example, and we'll be done for the day. All right. So we have this spool and the telephone wire wrapped around its core, and they have a total mass of 80 kilograms and a radius of gyration of 0.3 meters. If the coefficient of static friction between the spool and the ground is 0.4 and the kinetic coefficient of friction is 0.2, determine the angular acceleration of the spool if the end of the cable is subjected to a 30 Newton force. One of the things I want to get out of the way is find out what my mass moment of inertia is. Once again, they gave us the radius of gyration. So we take the mass times the radius of gyration squared, and we get a lovely 7.2 kilogram meter squared. Okay. Something we want to know is what is the criteria of whether the thing will slip or won't slip, because we're talking about the coefficient of friction here. We had the static coefficient of friction and kinetic coefficient of friction. So that's going to tell us, like, hey, will it slip at the connection point between the ground? So we know that if the friction force, the actual friction force, is less than or equal to 0.4 times the normal force, it doesn't slip. But if it does slip, the friction force is going to be 0.2 times the normal. So we want to try to find that out here. And if it does slip, the velocity at the floor does not equal 0. Otherwise, if it doesn't slip, the velocity here is going to be 0. Okay, so let's take the sum of the forces in the y direction. I think before we do that, it would make sense to write out or to draw up the free body diagram and an inertial diagram. So here we go. I'll write that in black here. So here's the free body diagram, and here's the inertial diagram. Here's the centers of these two things, and we're going to set these equal to each other. Free body diagram and inertial diagram. Set the directions of the things here. And I'll apply, let's see. I'll draw my center of this thing. And here are the forces acting on the thing. We have the normal force and the friction force. I'll talk about the direction of the friction force in a second. Here is the force of 30 newtons being applied to the piece, and here is my weight, which I'll write as mg. And it will have an acceleration through the center of gravity of mag, and in agreement with it will be the moment of inertia about the center of gravity times alpha. Now this friction force is pretty important to note here. Let's see, I guess I'll go red. Which direction should the friction force go? Sometimes we think about the friction force being opposing motion. But here we need to think about it a little more closely when we have a wheel that's spinning, right, and a wheel that's moving the thing along. The wheel itself will impart a force onto the road. I like to draw it a little bit like this. This is not a correct free body diagram because this is the force of the wheel acting onto the road. Well, we know that the road will instead impart upon the wheel an equal and opposite direction force. It's not necessarily equal. Well, I guess suppose, okay, I won't make that statement. But anyway, we want to take a look at the friction force, and it's going to be in that direction, suffice to say. So in the y direction, this is going to be no acceleration in the y direction, so that's really just a statics problem. So we could say that Fn minus mg is going to be equal to 0. So Fn is equal to mass, which is 80 times the gravity, which is 9.81. So Fn is going to be equal to 784.8 newtons. Now we could say that the friction for the static, so this is going to be the static case up here, we have to determine if that friction right here is, the criteria is going to be 784.8 times 0.4, right? It will end up being 313.9. That's the criteria, right? That's not necessarily going to be the friction force. Now, the kinetic, friction is going to be equal to 784.8 times 0.4, which comes out to 157.0 newtons. Now that will be the friction force if it slips. So to be able to find the friction force here, we could take the sum of the forces in the x direction is equal to mass times the acceleration of x. And we could say, okay, well, the friction force plus 30, so they're in the same direction with each other, it's going to be equal to the mass 80 times the acceleration g, right here. And now we have two unknowns, though, so we need to have something else. So we'll end up with the sum of the moments about g equal to ig times alpha. And we're making counterclockwise as positive. So we take the friction force times 0.75, and that's positive because it's going counterclockwise. So 0.75. And the load that's being applied to it, that 30, is in the clockwise direction, times 0.2. And so that's negative. It's going to be equal to the mass moment of inertia times alpha. Now that's acting in the negative direction. The mass moment of inertia is 7.2, and that's going to be times alpha. We could establish that a relationship between the acceleration and alpha right here, as long as there's no slip. So if you assume there's no slip, the acceleration of g is equal to r alpha. Okay, so we're going to have to go to the next slide to be able to continue this. And if that's the case, we could we'll rewrite our friction as 80 times 0.75 alpha minus 30 right here. Okay, so we've substituted in for the x direction, we've substituted the r alpha into for the ay. All right, and then we also okay, so we could also rewrite our moment equation as writing the friction force was equal to negative 7.2 times alpha plus 30 times 0.2, remember that was the load that was applied, divided by 0.75. We can equate these two things, and we could find that alpha is equal to 0.5460 radians per second squared, which is what we were trying to find. and that's going to be in the clockwise direction as we assumed. But we need to check something right here. We could plug this alpha back in and find that the friction force is going to be, I'll just put the numbers in here, 0.75 times my 0.5460, right? And then subtract out 30, and we end up with 2.759 newtons, and therefore no slip. So the assumption that we made, where we said that AG was equal to alpha R, that's okay for us. If it weren't, we would have to do some more work. But we're okay in saying that the alpha is equal to 0.546 radians per second squared and clockwise. So that's the answer. Now here is a what if statement here. What if rope, I'm going to say what if the rope is wrapped the opposite way? Well, we're going to have to start from scratch, or maybe not entirely from scratch, but we will definitely have to draw another free body diagram and an inertial diagram. So the free body diagram and the inertial diagram, there's our x and y, and there's positive here. All right, so we'll apply our loads, or have our loads applied for us, of Fn. Once again, frictions to the right, and we're going to have our mass times gravity here. And I didn't do a very good job of labeling this or leaving room for myself, but right here is going to be our 30 newtons acting that way. Now our accelerations are going to be mass times acceleration in the at G, point G right here, and we'll also have, once again, the mass moment of inertia times alpha. Now everything is the same for the in terms of the slip criteria, but let's go in the x direction here. So the sum of the forces in the x direction is equal to mass times acceleration in the x direction, and we have the friction force plus 30, right, is going to be equal to 80 times the acceleration g here. And I've assumed that it's going to be moving to the right, by the way. We'll take the sum of the moments about g is equal to the mass moment of inertia about g times the angular acceleration. So we take the friction force times the moment arm, and now we're going to go, it's going to be positive again. Well, this is going to be positive. It wasn't positive last time. 30 times the moment arm, or 0.2, is going to be equal to a negative 7.2 alpha. Once again, we assumed the direction is going to be clockwise here. So as we go through here, we're going to replace this alpha right here with, or let me say the other way around. We're going to replace AG with R alpha. Okay, so we say that the friction force is equal to 80 times 0.75, that's the R, times alpha, should be plus 30, I believe, right? Plus 30? No, it should be minus 30, because we're bringing it over to the other side. So it should be minus. It should be neater than that. Don't be like me. There you go. Minus 30. And we also can say from up above here that we could isolate the friction force, say minus 7.2 alpha, and this time it's going to be a negative because we're moving that 30 times 0.2 over to the other side, divided by 0.75, and we can equate these two friction forces here. And if we do that, we're going to find that it has an alpha of 0.3161 radians per second squared. And that is still going to be, let's see, did I do this wrong? Double checking. No, we're fine. We would find that it will be a positive number, so we assumed it the correct direction. We want to check our friction force, and that's going to be plugging it back into this equation. 80 times 0.75 times our 0.3161 minus 30, and it's going to equal a negative 11.063 newtons, which is less than 313 newtons. So there's therefore no slip. Interesting, though, that the friction force is going in the opposite direction. And we'll have the answer of 0.316 radians per second squared in this direction. Okay, that's it for me for today. I think everything is correct right here. I'll double check on them. I'm looking at some of these numbers and the direction of the friction force. I'm a little concerned by that. So, but that's at least going through the process. That's what that's how we're putting the thing together. So thank you very much, and have a good one. Hopefully this helps.